MacMaths, let's do some maths today. Okay, we're back to constant acceleration for this very last lesson in the Mechanics AS series. I haven't written that there, AS Mechanics. I always have that written in the corner. Okay, so the chapter 11, the last chapter of the textbook, goes through, is about variable acceleration, and the very last exercise talks about back to constant acceleration formula, and really it just, I think I might have done it on one of my previous lessons or at the start. It just reminds you this chapter that differentiating down from displacement to velocity to acceleration and integrating up, you can do that whether it's constant acceleration or not. And it just reminds you at the very end, going back to Newton's equations, that you can do it for his equations as well. And that is simply that if we start with the acceleration and we integrate that, well, that integrates up to the acceleration with respect to t, so we integrate it up, so that's just a number, so it just becomes that plus a constant on the end, and we know that that is the velocity. So we have the acceleration, we integrate it up, and we get v is equal to at plus this constant when we integrate it. But we also know that at t is equal to 0, okay, right at the very start, then the velocity is equal to the initial velocity. And so if we put t as 0 and v as u in there, we get u is equal to 0, because t is 0, plus c. So therefore c is the initial velocity. So then we can change this for u. And there's, putting all that out now, you've got v is equal to u plus at, and that's what we have for constant acceleration. And then again, if we integrate this up, okay, to the displacement, so we integrate going up, this becomes ut, and we add 1 to the power and divide by the new power, okay, and you recognise that formula, s equals ut plus a half at squared, that's that formula. There's a plus c on the end there, but obviously at the start of the simulation, when t is 0, the displacement is also 0. So putting t is 0 into there and s is 0, then c is 0. And so that just goes. Okay? And there you have, not written it very well as we go up, should have done it on this side. Just changed the way that looks, it's just the half at squared. And it just reminds you of that at the start of the exercise with an example. We'll come on to one of the questions that I'm going to go through that is like that in a second. Okay, so the start of exercise 11e. So this really now is just some support with the questions. There are 6 questions in all, and they're very straightforward, the first ones. I'm just going to jump straight to question 4. For you, and then I'm going to do question 5, which is a bit odd really. I'm not sure whether I do that the way that they intend it, and question 6, which is the last question of the exercise, and typically the hardest question. And this one here just says, question 4 jumps in and it gives you a, b, c, d, e, 5 equations, and it says which of these equations for displacement describes constant acceleration. Now then, constant acceleration means that your acceleration is just a number. I don't know, like 7 meters per second to the minus 2. That's accelerating quite fast. So constant acceleration is just when you just have a number. It's not going to change. It's not going to change with time. It just stays at 7 meters per second squared. So every second it increases its velocity by 7 meters per second. So the back of the book, if you look at the answer at the back of the book, what they do with all of these is they just differentiate them twice to see whether you get a number. So for instance, s, as soon as you start to differentiate that, 6, it just goes. So so that's not 1. But there's another way of doing it, of course. If you think about what we've just done, that acceleration, if you go the other way and that is just a number, that just becomes, when you integrate it back, it becomes at plus a constant. And then when you integrate it again, it becomes a half at squared plus that constant times t plus another constant. That's that formula, s equals ut plus a half at squared, when we sort out our two constants here. But really, these constants can obviously, c and d are constants, and they can be 0. So the important bit about this formula, for it to have a constant acceleration, which we started with, is that it has a t squared in it. So it's not going to be that one, because that's got a minus t cubed in it. That's a linear, so it can't be that one. And there it is, a quarter t squared. So that, if you differentiated it twice, it would give you a constant number there. And this one, of course, oh, that's just a weird one, that one. That's a t to the minus 2, isn't it? So, and that one, you know, it's nonsense as well. So you can see straight away it's this one here. You know, you're looking for a formula that's got the t squared in it. Okay, that will give you a formula with constant acceleration. But differentiating it, that's what they've done in the back. Differentiating all of those, you're looking for the one that differentiates to just a constant number, and it's this one here. And we just do it, s is equal to a quarter t squared. So if we differentiate that to get the velocity, you get, of course, 2/4, so you get a half t, and then you differentiate that and you get a half. So the acceleration there is a half a meter per second squared. Okay, so that's the one, constant acceleration, and the only one. So that was number 4. Number 5, again, number 5, yeah, I don't know whether I've done this one with the intention that they've done it. It's a bit of a funny question. It says a particle moves in a straight line with constant acceleration, yeah. The initial velocity, u, is 5, and after 2 seconds, it is moving with a velocity of 30 meters per second. So starts off at 5, okay, that's at t is equal to 0, and when t is equal to 2, the velocity is 30 meters per second to the minus 1. Find the acceleration of the particle. Well, that part A is not a problem. You can see actually just from there, it's moved from 5 to 13, so it's changed by 8 meters per second. And it's done that over 2 seconds, and because it's constant acceleration, 8 divided by 2 is 4, so every second it's changing by 4 meters per second. So the acceleration is 4 meters per second squared. Okay, that's the acceleration. It's changing by that every second. Another way of doing it, of course, is just to use v equals u plus at. So the initial, the velocity is 13 when the initial velocity was 5, plus the acceleration. We don't know that yet, but we know it accelerates over 2 seconds. So 2a, take off 5, and you get 8 is equal to, let's write that the other way around, and then divide by 2, and there you go. Acceleration is 4. Okay, so we've got that, and we used it, whether we did it just by thinking about it or we did it by using an equation of motion, we've got that the acceleration is 4 meters per second squared. We've got that. Now it's this next bit here. It says without using the kinematic formulae. So that's saying it's not using or just going straight and using Newton's equations that we know. Show that the displacement of the particle from its starting point is given by this equation. So I suppose here it's saying start with, so I'm going to do this the other way up, so I'll do it from the bottom. We're starting with an acceleration of 4. We know that the velocity integrating up is going to be 4t plus c, but we know that that c is the initial velocity, because we know that when the time is 0, the velocity was 5, so we know that that is 5, so we can change that, plus 5. So we can put 5 plus 4t there. Okay, so that is the velocity, and then if we integrate that to s, we get, well, I should have written that the other way around, shouldn't I? We get, this is that becomes 5t, that becomes t squared over 2, so that 2t squared plus a c on the end. Okay, so let's just by integrating we get that, and we know, but we also know that s, the displacement is 0 when t is 0, which means that c is 0. So we get s is equal to 2t squared plus 5t plus 0. Okay, so that's just from integrating from your acceleration of 4. Now it says, I did this sort of different ways, I did drawing a little diagram as well. It says, without using, find the displacement from the starting point is s equals pt squared, so it wants it in this form, pt squared plus qt plus r, and we can, where p, q and r are constants to be found, well, we've found them, haven't we? P is 2, q is 5 and r is 0. Another way of looking at it is to draw a little diagram of what's happening at the first here. If we draw our little diagram there of 5 and 13 after 2 seconds, I also did that. So this is 13 here, this is your velocity time graph, okay, and after 2 seconds it's travelling at 13 meters per second, and at no seconds at the start it's travelling at 5 meters per second. And if you draw a little diagram of this here, you've got a trapezium. If you work out the area of this trapezium, you've got 5 out of 13, which is 18, divided by 2, which is 9, times the distance between, which is 8. You get the displacement over time is 18, and you can put 18 in there and put 2 into there. Okay, and if you'd still got that, well, do it into this one, if you still got the c on the end with 18 in there and t is 2 into there, that will all, this will be 18, all of that will be 18 as well, which makes that your c, your constant that we put on the end, 0 as well. You can do it that way if you want from this little diagram. I suppose if you did it that way, you're not using the Newton's formulas. Okay. I think they just meant you to do that though, you know, to integrate it twice, once to there and put the constant in as 5, because we'd already had that, and integrate it again and just relate. Okay, so that one was number 5. And then the last one, yeah, it's one of those, I like these questions. Okay, and you may struggle on this one, so I'll go through this one with you. Okay, so my advice is always to get a diagram in with these sorts of questions. Okay, makes it, you know, a lot easier to do. So here we go. A train, I'll just cover that up there. A train, just make sure that's in. Is it in the shot? Yeah, it is. A train travels along a straight track passing through A at time t is equal to 0. There it is. So it's there. And passing through point B 40 seconds later. That distance there is a time of 40 seconds. Its distance from A to B is given by the formula. So the displacement is 25t minus 0.2 t squared. Okay, between 0 and 40. Okay, find the distance AB. So all we do is put 40 into there. So 25 times 40 minus 0.2 times 40 squared. When we do that, I did it on the calculator earlier, you get 680 meters. So this is 680 meters. Okay, all right with that? So that's the first one, bit done. Show that the train has constant acceleration. So that's the answer to part A, done that one. Let's just rub that out. It says, yeah, it's funny this one. It says show that the train travels with constant acceleration. Okay, so the velocity differentiating down is 25 minus 0.4t. They've differentiated it to get the velocity, and if I differentiate again, dv by dt, that's the acceleration. So that goes, the t goes, and you get minus 0.4. So it's constant. It calls it constant acceleration. It's a negative number, which means that the train from there to there is actually decelerating. Okay, it's slowing down, but it's a constant deceleration. And of course, a deceleration is an acceleration. It's a change in with speed with time. Whether that speed is increasing or decreasing, it's still called an acceleration. We sometimes conveniently have this negative number as a deceleration. So we know the deceleration is minus 0.4, and we've shown that it's constant because we just get the number. And the second bit is the fun bit. Okay, so this is the thinking bit. So here, a bird passes point B at t is equal to 0. So when the train is here, a bird is flying here, and the bird is flying in a straight line in that direction. Now I might have paraphrased a little bit, but that's what's happening. The train is travelling in that direction, and the bird is flying in that direction. The bird passes point B at time t is now with initial velocity, so I'll put my bird here, and its initial velocity is 7 meters per second to the minus 1, and it flies in a straight line with constant acceleration. The bird is speeding up. Can you imagine? It's not very realistic, this, is it? The bird is speeding up in that direction towards the train, and the train is slowing down in that direction. Find the distance from A that the bird is directly above the train. So where do they actually sort of meet doing that? Okay, so this is going to be setting up, we've got an equation for the train, we need to set up an equation for the bird and solve them simultaneously to find that time. The best way of doing this is to put your point on where they cross on here. So they're going to cross somewhere, let's say they cross here. Okay, the distance the train is going to take to reach there is s, the displacement from A. So it's that. Okay, so the train, we've got our equation for the train. The equation for the displacement of the bird from this point, okay, so ignoring the train, we're looking at displacement for the bird. So what is the displacement of the bird? Well, s equals ut plus a half at squared. Okay, so the displacement of the bird is its initial velocity, which is 7t, plus a half of a. So I'm going to go straight into this. A half of a is a half of 0.6, so 0.3 t squared. Okay, so that would be the displacement of the bird from B. But we don't want it, we don't want this distance. Well, we do want this distance, but we want this distance described from A. And the distance, this distance here, of course, is 680 meters, okay, minus this figure here, isn't it? So whatever that distance that the bird flies, that this formula is finding here, we want 680 meters minus that, and that will give us this distance here, the distance from A. So we want 680 minus s, okay, and that describes the displacement from A, doesn't it? Okay, because s is the displacement from B, which is what this formula has given me, and 600 minus s would be the displacement from A, is 7t plus 0.3 t squared. Okay, so now we've got two equations and two unknowns. All right, so what we're going to do is I'm just going to rearrange this. I'm going to put the s onto this side and move everything across onto that side. So I'm going to go, well, actually, I'll move that over there and multiply everything through by -1. So if you did that, and I've got plus 680 actually. Okay, so that's our equation. This is just this rearrange. Sorry, I did that all in one go. So just be careful that you rearrange this correctly. You can see what I've done. I've taken that over there. I've got a positive 680, a minus 70, and a minus 0.3. So now I did that so I can just put these equal. So now my whopping great equation is just S equals, it's not. It's putting these two equal, so we've got 25t minus 0.2 t squared is equal to minus 0.3 t squared minus 7t plus 680. Okay, and if you rearrange all of that, you can take that over to there, so you get 0.1 t squared plus 32t minus 680 is equal to 0. Times everything by 10 to get t squared plus 320 t minus 6800 is equal to 0. Okay, and actually you could, that does factorize, but okay, you wouldn't, you know, I would just go stick in minus b plus or minus the square root of, and if you did that, you only want the positive value for time, don't you? You don't want, you know, some meeting over here, because these are quadratics, so you only want the positive value, so you only need to do minus b plus the square root of b squared, 320 squared, minus 4 times 1 times minus 6800, and you've got your minus and minus, so that's plus all of that, all over 2a. And if you did that, and I did it before, you get a time of 20 seconds, which means train and bird meet here after 20 seconds, so actually at the halfway point in terms of time. All right. But then you have to, it's not linear, okay, so that it is a quadratic, so it's not half the distance, it's just half of the time. So then you have to put your 20 into either of these equations. Okay, so if you did s is equal to 25 times 20 minus 0.2 times 20 squared, and if you did that, if you substituted that into there, you get a displacement from A of 420 meters, which is the correct answer. Okay, and I hope that makes sense. And that is the end of the mechanics for AS. I've done a series of the learning timetable, so those are your homeworks, and I've done sort of 6 for you, but I'll start to put those out each week, and it's just 3 questions a week, but I'm going to put those onto YouTube as well for you, okay, with the question sheet, and it's just going to be mixed questions from all of those chapters that we've covered. Okay, and that's it. That's our mechanics done for this year.